going to be talking about BIF-hosted iron ore from a mineral systems perspective. So in the last 10 years or so, there has been a lot of attention in the Hamersley Basin. And by these red dots here, you can see why. Basically, a lot of these large iron deposits are located in this province. But as the dollars were attracted to neighbouring areas, also research attention was also attracted to these locations. So that led our group to then focus on what are controlling these BIF-hosted iron deposits in the Yilgarn and in the Pilbara. At the same time, our colleagues in South America were also looking at these major examples in Carajás and the Iron Quadrangle. And so this leads us to be able to build a set of comparative databases, which hopefully we can condense together in terms of generating mineral systems understanding, which will help exploration in terms of prediction and detection of these types of deposits. So basically this is where we've started off on the left-hand side. So a number of genetic models, a lot of them are competing, so we can perhaps look at Mount Wellback as an example. And there are a number of competing models. Perhaps the Vasaro model of the 1980s versus a more recent edition of a genetic model, which is a hypergene model. So in some areas these are competing models, but in other areas of the world perhaps these are the style of deposits which are present there. So we have to be mindful that they're not always at loggerheads against each other. But basically, multiple genetic deposits equals complexity. And so how do we simplify that into a mineral systems understanding? So for the last 5 years or so, we've been trying to come up with common threads amongst these different genetic models and try to develop a mineral systems understanding. So for today, I guess you've looked at high value economic deposits like gold and nickel. Now how does a bulk commodity mineral system look like? You can ask that question to yourself, and for the rest of the talk of today, I'll just run through what I think a preliminary model might look like. I'm going to divide this talk into 3 components. The first one is to just briefly present key concepts in BIF-hosted iron deposits. So basically, we should be on a common playing field. After that, I'll review 3 of the common genetic models: syngenetic, supergene metamorphic, and supergene modified hypergene. We don't want that. Explain that. And then I'll conclude by presenting a preliminary mineral systems model and what the implications are for exploration. So put very simply, the genesis of BIF is understood. It's quite an eloquent model in that BIFs are chemical sediments, where the repository of the iron and silica was seawater. In a reducing environment, the iron is soluble as Fe2+, and silica is dissolved within the seawater. When the atmosphere became oxidizing, the Fe2+ was oxidized to Fe3+, combined with oxygen, and it precipitated in some of these environments. And to benefit the mixing of the Fe2+ with the oxygen, currents along these basinal settings would combine oxygen with iron to precipitate the iron oxide. So this process is tectonic driven. It's controlled in terms of age. The great oxidation event in the Earth's history was a main driver, and also the tectonic settings. So periods of the Earth's history when there are large basinal settings were very good for depositing thick and iron formation. We can divide these BIFs into 3 main types, shown here in this schematic. What I showed you before is quite well suited to Lake Superior type. So a basinal environment, we form these Superior type BIFs, and they are underlain by classic sediments. We can also recognize these greenstone belt-hosted BIFs. These are underlain by mafic rocks. And then lastly, there's Rapitan type BIF, and they are quite small in terms of volume, and they've got a special feature in that they formed in lake environments at a time where iron could concentrate in the lakes. It was separated from the oxidizing atmosphere, And when these glaciers retreated, we now let the iron become in contact with oxygen, and then we have the deposition of these banded iron formations. Where do they occur within the world? What I show here are these cratons, and within a craton, the blue is the Archean crust, and the yellow is the Paleoproterozoic crust. Not all of these cratons have large iron deposits, so that tells us that, yes, we can be in the right area within the world, which is areas of stable and all crust, but still we don't have these large iron deposits forming. So why is that? There must be some other critical elements missing. This is the flavour of iron ore. So on the top, magnetite rich, crystalline hematite rich ore, and on the bottom, goethite hematite ore in different forms. And what we find is that these deposits are generally hybrids. So basically, there are these blanket-style mineralisation of the goethite and hematite, but they are overlying deeper sources of iron, which are the magnetite and hematite. So a lot of these competing genetic models are not debating the genesis of the recent goethite overprint. What these competing genetic models are arguing about is the source of the magnetite and the crystalline hematite. And what I'm saying is that these giant iron deposits require both. If you think of Mount Whaleback or Mount Tom Price, it's official goethite hematite overlying magnetite microclady hematite. So it's important to have the coincidence of both types of iron ore. So I've sort of talked a little bit about BIF and its occurrence and what it looks like. Now what about the iron ore? So how do we go from something like this on the left, which is primary BIF, to the different forms of iron ore? The middle one is magnetite rich, and the right-hand one is goethite hematite rich. There are three simple ways to do that. One is to remove the silica gain. So we can do this in Photoshop. If I would just edit out all of the quartz, I would get a volume reduction and something like this. Another way is to actually in situ replace the gain by other iron oxides. And we're going to get something a little bit like this. It's more, the texture is a primary BIF, and the silica has been leached out and replaced by goethite. And then lastly, we can actually add new iron oxides to the rock. So we can dissolve iron from deeper down in the BIF, transport it, maybe as a reduced iron, and then deposit it. And that's a way of increasing the iron content. And how do we do that? We need fluids. Either supergene fluids in the case of our superficial deposits, or hypergene fluids in the case of the magnetite, crystalline hematite fluids. Okay, for the middle part of my talk, I'm going to discuss these three competing types of genetic models, starting off with the syngenetic type. So the key thing about the syngenetic type is that these iron ore deposits formed at the same time as the actual BIF. And then on top of that, there is subsequent enrichments due to the supergene processes. So all of these three competing genetic models, they all have this last supergene enrichment. So that's not what I'm going to really talk about. I'm talking about what's causing this early hypergene mineralization. So in the syngenetic models, it's envisaged that the BIF formed as a layer of gel-like materials. So iron hydroxide and a silica-rich gel, this nongenite, mostly silica and OH ions. And a breakdown of nongenite to form iron oxides, as these little red dots, and colloidal silica. These little red dots accumulated to form our future iron oxide bands and separated with the silica bands. So that's fine, that's not forming our actual ore deposit though. So what happens if we had this layer system and we shook it up a little bit, perhaps impose some earthquakes? In this type of situation, we would have a structure developing and the release of this gel-like material. So in this case, water and silica are being removed, so, such as here, and then forming our chert-free BIF, surrounded by our cherty-rich BIF, and then if we were to erode it, uplift it, we would create something like this, and then we superimpose our goethite blanket on top. So that way we have our superficial goethite hematite ore, and then our deeper roots of hematite goethite. So this is a genetic model type 1. What is the implications of this are that they are primary ore bodies. They may exist below the weathering zone. They don't have necessarily surface expressions, and structures are not very important. Okay, genetic model type number 2 was championed by Dick Morris in the early to mid-80s. And put quite simply, what he envisages is upgrade in the BIF due to supergene processes during the Proterozoic. And this started from bottom-up type of enrichments. So it led to the substantial ion upgrade within the BIF until it stopped at surface. This mineralization, this martite goethite ore body was then buried during the Proterozoic and heated to temperatures of about 100 degrees centigrade, whereupon the martite goethite was transformed to microplaty hematite, and then this package was eroded and then superimposed on by our more recent supergene upgrade. Now the implications of this type is that the structures actually have a passive role. We don't really need structures in this situation. We just need the deep convection of near surface fluids to form our original supergene upgrade, and then its transition to the surface. And then importantly, hydrothermal alteration zones are not integral to this type of deposit. So we're not really expecting to see a big alteration footprint associated with our ore systems. Now, an alternate model is one which we have been working on for the last 10 years for the CET, and that is that we're trying to explain that these early magnetite, hematite ore bodies are the products of hypergene fluids going through the BIF, and then followed by the supergene upgrade near surface. So this results in the magnetite, spectrite, which is crystalline hematite, and also microplaty hematite ores. And then this system has been exposed and then superimposed by the supergene ion enrichment. So one of the driving forces for this type of model is a cross-section for Mount Tom Price, but it can be related to Paraburdoo and Mount Whaleback. But at Tom Price, it's quite nice in that we can see magnetite ores, microplaty hematite ores, all located below the weathering front. And on top is the superficial goethite hematite mineralization. So the supergene metamorphic model would show that any alteration within the footwall is accidental or post-dating the formation of these magnetite hematite ore bodies. But what we do see is that underlying these iron ore deposits is some chloride alteration and also carbonate alteration. So there is a hydrothermal footprint, and we see that they are coeval with the magnetite. So we don't think it is an accident that we have these carbonate alteration, chloride alteration in association with these magnetite and hematite ores. And looking at some of these fluids, which are trapped by the carbonates, for example, they are high temperature and hypersaline fluids, so indicating that they're not just meteoric or metamorphic fluids. So what we'd imagine the implications of this model is that our ore body would have a nice hydrothermal hypergene alteration halo within the BIF, shown in this greenish unit here, but also in the underlying sedimentary rocks of shale, like this chloride alteration. So this is actually very good for our exploration. Provides our important targets for vectoring to these systems. So that's it in a nutshell of the three types of genetic deposit models for iron ore. So how do we go from this rather confusing situation to something where we actually just highlight the importance features of these deposits? And I think that is the biggest contribution of the mineral systems model. So we've got a running model at the moment, which has got the same structure as other mineral systems model, broken down into the key elements on the left-hand side. And I'll just pop up what we see as being the critical parameters. And instead of going through these sequentially to death. I'm going to just go through the main criteria in a number of slides. But I'll just preface that by mentioning BIF fertility. Not all BIF is created equal. We've heard that in terms of other commodities today. Structure is important in terms of thickening the BIF and putting fluids where we want them to be. But we don't want just any old fluid. It has to be silica undersaturated. There's no point pumping a silica-rich fluid through BIF. We're never going to find a high-grade iron ore body as the result of that. We need to uplift these hypogene ore bodies to surface and hit it again with another fluid, an oxidized fluid, to form the supergene imprint. And then we need to preserve it. So in your notes, I've got this in detail for you to read later. So number one, BIF fertility. What we don't really want is a cherty-rich BIF. It's easier to form the end product, which is rich in iron, from one that looks rather like an iron deposit to start off with. So casual observation would show in some camps we see BIF which are not mineralised. In this case here it's from World Range, and I'm showing the central BIF, which corresponds to the long beds. Basically it's all cherty BIF, whereas the flanking BIF macro bands, the Madunga and the Wilkie Maya, are more like this example here, and they have most of the iron-enriched occurrences. So why is that? Another observation is that on the scale of the Yilgarn, when we look at the distribution of our primary BIF in pale blue and our enriched BIF areas in red, they are all along the western side of the Ida fault. So again, why is that the case? It looks like there is a first order control on these BIF-hosted iron ore deposits. What I have done is I've looked at the GSWA maps and I've just shown examples of BIF within the Yilgarn. And for comparison, I overlay the same MindX data set here. And so what you can see, at least from a first point of view, is that the BIF is more abundant on the western side of the Ida fault. And it is generally thicker. And I think that is a step in the right direction for controlling later iron enrichment. If we compare it to where we think the paleocratonic boundaries were at around about this age, bear in mind that the BIF that we've looked at in this area is about 3 to 2.8 billion years in age. Where these paleocratonic boundaries occur, that's where we have a lot of these thick BIF. We also have the future enrichment in iron as well. So quite a testable hypothesis is that perhaps these paleocratonic boundaries are very important in forming these thick BIFs, and it's the perfect starting point to form our later enriched iron deposit. Okay, second critical element is structure. In this case here, we can break it down into two types. One is that it's a lot better to work with a folded BIF than it is with a BIF of its primary thickness. And in this left-hand side part of the slide, you can basically see the primary thickness of a BIF in the iron quadrangle in Brazil, and then its folded versions in the fold hinges. And this section through here is showing that it's a fold interference geometry of this area here being the BIF. So perfect. We can duplicate the primary thickness by folding and also by structural dislocation, potentially. So the second important criteria with the structure is that we need to move fluids, and a lot of fluids through BIF. So some examples in the Brockman Formation in the Hamersley province from Mount Tom Price, Parabadoo and Mount Wellback. In these two cases here, the deposit stratigraphy has actually been back-rotated to the geometry at the time of mineralisation. And you can see that each locality has some first-order structures. And what we envisage is that these structures are the primary channelways for these hypogene fluids to move up, hit the BIF, and remove the silica and move onwards. In this case, the structures have had an active role in that they've been deforming the BIF, and fluids have been focused within these structures. But the structures can also have a passive role. So in the case of the Marramamba example, we have the early duplication of the BIF, but these can be in a more passive control in that near surface fluids can just percolate downwards and react with the BIF. Okay, the third critical criteria is that we need lots of fluids, and it has to be the right conditions. It can't just be fluids such as those forming gold deposits which form in quartz veins or add silica to the rock. So we tried to constrain that with fluid inclusions. I've shown two examples here, one from the Yilgarn, one from the Hammersley, and I could have shown another from Carajás in Brazil, but for simplicity I'm just showing Yilgarn and Hammersley today. So these early fluids, which are forming the magnetite-rich type of ore, they're hot and they're hypersaline. And so what they're doing is that they are adding carbonate and magnetite. And the carbonate is replacing the silica gains. So these silica primary bands are being replaced by carbonate, and then they are then going to be leached by cooler fluids, which have the meteorite water signature. And they remove the carbonates, and the end product is a iron-rich BIF. In the Yilgarn, which has a lot of the specularites, such as Kulinobbing, very large crystals of crystalline hematite there. They also record fluids which are lower temperature and hypersaline fluids. We don't seem to see them so much in the Hammersley. So if we were to try to sort of compare this on a common platform, we've come up with this type of diagram, which is explaining early hypogene fluids, which are forming these magnetite-rich ore bodies. So where would these provinces fall within this diagram if we break it into basinal fluids, metamorphic fluids, and magmatic fluids? Carajás, which unfortunately I didn't have time to show the data, but there is a very strong evidence to show that these fluids are sourced from a lot of these felsic plutons which are in the Carajás district. And these fluids are hot, they're hypersaline, and they've got all the hallmarks of having a component of felsic fluids. If we look at the Hammersley province, work from Warren Thorne and others have looked at these magnetite-rich ores and have looked at the fluid inclusions and show that they're hot, hypersaline, and the cation ratios have the indications that it's most likely a basinal fluid has been important in terms of forming this type of ore deposit. In the Yilgarn craton, again we have hot temperatures, hypersaline fluids, but the timing is quite late. It's about 250 million years after BIF formation. We have dated some of these hypogene magnetite ore bodies, and they're about 200 million years after the formation of BIF. So ruling out basinal brines as being part of that. So that's why we envisage at this stage these Yilgarn deposits are between the magmatic and metamorphic fields. So we lost control of the mass. Okay, so a lot of these hypogene deposits are then overprinted by specular hematite or macroplated hematite. In the Hammersley, in the Yilgarn, and Carajás. So in all of these different areas, it seems like we have another fluid which is still warm, medium temperatures, low salinities, and that is an overprint. We have the mobility of iron forming these crystalline hematite. And then lastly, we have the overprint of the supergene goethite blanket on top of these hypogene ore bodies. Okay, so fourth critical point is superficial modification. It's one thing forming these hypogene ore bodies, it's another thing trying to get them to the surface when they're hit by the supergene fluids. So, of course, we have to exhume them, both the BIF and also the hypogene ores, but we can't exhume them so much that we actually remove their presence. So, we need that sweet spot in their exhumation. And then typically they're buried. An example is from Mount Richardson here, where we have weathered mafic rocks and then magnetite-rich BIF, and it is, in this example, blind. It is covered by superficial material. So then again, we have the issues of bearing. And we need to have a lot of supergene modification, which will cause ion enrichment and removal of phosphorus. And it's best that all this is happening at paleolatitudes where there's a lot of water and a lot of stability for long-lived supergene alteration. And then the last critical feature is its preservation. So we can have the hypogene ore, we can have the right fluids, the right structures, they can be eroded to the right position, but if they're generally a very soft, friable material, which are very easy to then erode away. So the best situation is to have a hydrated zone, which is a hard cap on top. It can be relatively thin in terms of metres thickness, but in the case of West Africa, it's very important in that it has preserved the friable material underneath. Graben structures are locally very important. For example, at Parabadoo, where the down throw area is where the ore sits and it's been uplifted. If it were the reverse, that it's been thrusted up, then we can find that we're missing this ore body. And it's also important that we don't have long-lasting glacial processes, which is going to remove these superficial deposits. So the conclusion is essentially that there are a number of genetic models. Locally, there are cases where they're competing. We can pick one deposit of interest, and then we can argue to death whether it's the Dick Morris model or the hypogene model. But what we're trying to promote nowadays is that these are alternative models. So somewhere in the world, they could be valid. So we have to be mindful of that. Most large iron deposits display both the supergene alteration on top of deeper, older hypogene ore bodies. Very few large deposits form just through one type. The mineral system model is very handy for simplifying quite complex situation. BIF fertility is very important in terms of having the right composition, the right thickness to start off with. Structure is important in terms of fold thickening, and then later transport of fluid through the BIF, leaching the BIF of the silica. We need to have the right fluids, that they can't add silica to the BIF, and sufficient modifications, preservation are crucial as well. So in comparison with other mineral systems, I guess the bulk commodity system requires a lot of fluid and it has to be acting in a broad sense. Unlike the gold system, where we can have a lot of fluid going through a metre thick structure, that doesn't work with our large bulk commodity system. We need to have pretty much that amount of fluid going through tens of metres of volume of rock to remove the silica. Unlike gold, or potentially nickel, it's a mass negative process in that we're actually removing stuff from the primary rock to form our ore body. And the key thing is that these giant ore deposits are multiple superimposed systems. It's like our gold deposit. We need to have the gold on top of VMS, so we have to have the coincidence of all processes to get our large, high-value deposit. And I don't think it's an accident. I think these structures are long-lived, they're early, they're hit many times, and these fluids have been focused time after time to cause this ion upgrade. The Uncover initiative is important not only for gold, nickel, but also for iron ore. Who would have thought? I guess in terms that a lot of these deposits are now covered, we're looking to unusual areas, and the signature of these deposits vary. Sometimes they're magnetic in terms of magnetite, sometimes they're non-magnetic in terms of goethite. So it's quite complicated to find them undercover. So the mineral systems model is actually quite important for working out what are the critical factors, translating them to mappable features, and then being able to target these different iron ore styles at early stages of exploration. Thank you.
Thanks a lot, Paul.
Yep.
Good presentation. Do we have any questions? John.
So probably a dumb question, but how do BIFs form at rigs, in this high temperature volcanic? I guess that's your Algona type. Like the model of kind of the reduced iron being dissolved and transported to the platform and the oxygen down in the coating zone, that's fine for the platformal stuff. But I can't quite conceive of how BIFs are forming, as they are sometimes, coeval with these volcanics and obviously deep rifted volcanic environments.
Yes, that's right. I mean, they're certainly coeval with these magmatic rocks, and in this sort of environment, these black smokers are quite a understandable contributor of iron. And we form these sulfides or
So
iron.
where does the oxygen come from in that environment?
Yeah, I suppose, I guess you need to have some kind of interaction with oxygen. I suppose that you need to be able to get the oxygen from surface to interact with the iron to form the iron oxides and then rain these iron oxides out of the water. So I suppose that over time the iron is being enriched in this area to high concentrations, and then perhaps at the interface you're able to have that exchange with the oxygen to then deposit out. Yeah.
Any other questions? I've got one here. That question of John's is critical, really, because back in 3 billion years there's not meant to be any oxygen in the atmosphere. That's what the tells us, and therefore you really couldn't precipitate magnetite by that process. But I think probably what that is telling us is that there was oxygen in the atmosphere at certain times, back beyond 2.5, and that we were able to precipitate magnetite. But that's an intriguing question.
Yeah, well that's right. I guess the great oxidation event is well after these Archean BIFs are formed. So
That's that oxygen oasis concept.
yes. Yes, and these Algoma type deposits are that's a lot smaller than the superior type, so